In this video, we're going to talk about the idea of operating with cosets of a subgroup in a given group. So here's the big question that we're going to try to answer. The big question is, can we construct a group, a new group, from the left cosets of H, a subgroup of G? All right, so we're given a group G, we're given a subgroup H, and we imagine forming the left cosets of H. There will be some set of them, maybe finitely many, maybe infinitely many, who knows? But the question we want to answer is, could we operate on the left cosets of H so that they become their own algebraic objects that form a group, a new group? So just to give an idea of where we might have done this before, because this isn't a completely new idea. Even though it is a new way of expressing an idea that we've encountered before. So let's take G to be Z, the group of integers under addition. And let's say that H is, I'm going to say 4Z. That's a subgroup. Again, 4Z, just as a reminder, it's the set of all integers for n, where n is an integer. That's a subgroup because any two multiples of 4 add together to give another multiple of 4, and the opposite of any multiple of 4 is a multiple of 4. So the question is, or the first question is, what are the left cosets of H? So the left cosets of H are H itself, or if you like, 0 plus H, and that consists of integers like -8, -4, 0, 4, 8, etc. And then there's 1 plus H, and that would contain things like -7, -3, 1, 5, 9, etc. And then there's 2 plus H, and that would have -6, -2, 2, 6, 10, and so on. And then there's 3 plus H, which would consist of -5, -1, 3, 7, 11. You get the idea. Every integer is in one of these cosets, and these cosets are all disjoint from each other. I could construct 4 plus H, but that would be a repeat of 0 plus H. I think these make up all of the integers. These are the left cosets. So one thing we might infer from this is that the index of H in G, the number of cosets of H, is 4, which is kind of cool because we know that G is infinite, H is an infinite subgroup, so you might wonder, how can we compare the size of H to the size of G? Because, what is infinity divided by infinity? That could be 4, it could be something else, it's hard to say. But we can measure the size difference between G and H by thinking of the number of cosets. In this sense, we can say that H consists of basically 1/4 of G. But that's not what we're here to do right now. We're here to operate with cosets. So suppose I did this. Suppose I take 2 cosets. I'm going to change colors now. There we go. Let's say I take the cosets 2 plus H and 3 plus H and add them together. What would that look like? Well, one way of thinking of this is to say this is going to be the set of all A plus B, where A belongs to the coset 2 plus H, and B belongs to the coset 3 plus H. All right, so I can take any element of this set plus any element of this set. So I hope that you'll join me in taking a few sums of element of 2 plus H plus element of 3 plus H, and think about what you could come up with. I'm just going to do a few here. If I do -6 plus -5, I get -11. And I'm going to do this in a pretty unsystematic way. If I do -2 plus -1, I get -3. And then if I do, let's say, -2 and 11, I get 9. If I do, what else could I do? 6 and 7, that would give me 13. And yeah, I know I'm probably skipping some things here that I also could get. I don't mean to get everything that is in the set. I'm just trying to come up with a few examples of what might be here. What else might be here? Well, I could do 2 plus 3 and I could get 5. So there's probably going to be a lot more here. But I do notice that everything that I get that I have in this picture here, I have -3, I have 5, I have 9, 13 would have been just over here, -11 would have been just over here. Could I have gotten 1? Let's see. Oh, I could have done 2 plus -1. That would give me 1. So everything I'm getting seems to be in 1 plus H. And in fact, you could prove that the set that we get by adding these two cosets together, it actually is 1 plus H. Everything is in the same coset. So what this allows us to do, and I'm going to do this informally right now, we're going to define it formally later. What we're going to end up doing over this video and the next is we're going to construct something called G mod H. And this is going to be what we call a quotient group. Not because it is a group of quotients exactly, but because we think of it as a quotient of two groups, sort of like G divided by H. All right. And earlier we said that H consists of 1/4 of G. And that quotient group is going to consist of all of the left cosets of H. So in this case, 0 plus H, 1 plus H, 2 plus H, 3 plus H. That's going to be what's in this group. So this quotient group of an infinite group divided by, or mod, really the proper term is mod, another infinite group, an infinite subgroup, is this 4-element group here. Okay, but what's the operation? The operation is pretty much what we did here. It's take two cosets and add them together. Notice that what you get is another left coset. It's exactly another left coset, and that's the sum. So for example, 2 plus H plus 3 plus H is equal to 1 plus H. That's an example of an operation in this new group. And in fact, we could construct a Cayley table for the group. And you're going to have to probably trust me for now on some of these operations. I mean, you don't have to trust me. You could actually work out what the sums of elements in these cosets would be. But if I were to set this up, I would get 2 plus H, 3 plus H. Over here I got 0 plus H, 1 plus H, 2 plus H, 3 plus H. And because I think addition is probably going to be commutative, I don't need to worry about whether the columns or the rows are the thing that goes on the left, although customarily the add-in that goes on the left is over here, and the one that goes on the right is over here. But here's what I would end up getting if I actually worked out all of the cases. 0 plus H is going to turn out to be an identity. In other words, and let's actually take a closer look at this. Let's say I take one of my cosets, let's say 3 plus H, for example, and add elements of 0 plus H. What am I going to get? Like, I could get 3 plus -4, but that would be -1. That's right back in this coset here. 7 plus 4 would be 15. I don't see 15 here, but it's actually just to the right of 11 in this coset. So it seems like adding anything in this set plus adding anything in this set keeps me in this set. That makes this coset an identity for this new group. All right, if I keep propagating this Cayley table, here's what I'm going to get. It's going to turn out 1 plus H plus 3 plus H is 0 plus H, because any element of this set, like -7, plus any element here is a multiple of 4. That one gave me 4. Get 3 plus H, 0 plus H, 2 plus H plus itself is 0 plus H. We've already worked this one out. And then 3 plus H plus itself will be 2 plus H. So that's a Cayley table for this new group, a group consisting entirely of cosets. But wait a minute, we've seen this group before, haven't we? I mean, we've seen this construction before pretty much. It's just what I'm calling K plus H is what we used to call brackets K, the congruence class of K, in this case mod 4. So the group that we've constructed here really is just Z mod 4. So what we have here is that this quotient group, Z modulo 4Z, that's a formal construction of what we had informally constructed as Z mod 4. And we constructed originally using like clock arithmetic, and we did sort of think about these congruence classes, but we talked about how addition of congruence classes seems to be well defined, but we never really framed it in terms of cosets. Now we are doing that. And in fact, just as a fun little side note, what we call Z sub 4 in this class, many algebra classes and many number theory classes actually never use this because they want to use this type of symbol for something else called the p-adic integers, which is a different thing from what we're doing here. So a lot of the time they'll use this symbol only for Z mod 4. So there we go, there's a new idea. So I wonder what other settings we could do this in. So, I mean, do we only get to do this with integers, or can we do this with other types of groups as well? Let's go back to the example we talked about in the previous video where we had, I believe it was G equals S3, and we had H equals the subgroup consisting of the identity. There I am using, this is just epsilon. Let's just get that right from the outset. And then let's say 2, 3. So let's take that particular subgroup. And just so you don't have to wait for me to reconstruct all this, I'm just going to throw down all of the cosets at once here. There we go. I hope that you see that now. So I just figured I wouldn't make you wait 30 seconds for me to write all that down. So what if we tried the same game here? So this time we are using multiplication, or really composition is our group operation, so you don't see those plus signs anymore. But the idea is pretty much the same. So what I'd like to do is try multiplying two of these cosets. So pretend that these are things that I can subject to the same group operation I had earlier. All right, I'll use dot just to indicate that we are multiplying or composing two things. All right, what is that going to give me? So I'm just going to go through very systematically and multiply every element of this coset by every element of this coset. So we're going to get four things, which hopefully they won't be four totally different things. So let's start with 1, 2, 1, 3. I believe that comes out to 1, 3, 2. So that's our first element. Okay, what about 1, 2, 1, 3, 2? If I do that, then I'm going to leave you to do the multiplication yourself and verify what I'm doing. But I think I get 1 goes to 3, 3 stays put, and then 3 is going to go to 2, and 2 is going to go back to 1. Okay, and then I think 2 stays put. 2 goes to 1, then 1 goes back to 2. So far it looks like what I'm going to get is this coset here, 1, 3H. Let's verify that that works out. What if I do 1, 2, 3 multiplied by 1, 3? Well, then I get 1 going to 3, 3 going back to 1. So 1 stays put. I believe 2 goes to 3, and 3 goes back to 2. Okay, that's an uh-oh, but I'm going to go ahead and do the fourth product just so it's a little bit clearer why it's an uh-oh. And that's going to be the identity, because those are inverses of each other. Now look at this. This time I multiplied two cosets, and what I got, I mean, I certainly got a set, but I did not in any way get a coset. I got what looks like two cosets jammed together, this one and this one. Okay, so that's curious. So in this case, multiplying left cosets does not give me a coset. So let me write that down. In this case, multiplying two left cosets did not give a left coset. A left coset. So if I'm looking to define some new algebra with cosets, like a new group whose elements are cosets, I am not going to be able to do that here, at least not in the way I conceived earlier. And it turns out that the thing that's getting in our way here, the thing that is jamming us up, is that if I'm trying to define this in such a way as to get a coset, I have a real problem here. Because one thing that would help greatly in turning this into a left coset, this thing here, I mean, one way I can think of this is it's a product of two left cosets, 1, 2 times h times 1, 3 times h. But really, this can be any element of h here. Like this is a set, and the set has this specific permutation times any element of h times this particular transposition times any element of h again. So what's in the middle here is a member of a right coset, h times 1, 3. One thing that would help greatly would be if I could turn that around and turn it into 1, 3 times h. And then what I end up with here is some element of h times some element of h. So that's really just h. Like if I say what's the set of all products of thing from h times thing from h, that's really just h. So that would then be 1, 2, 1, 3, there we go, 1, 3, h. And then that would work out to 1, 3, 2, h, which is kind of like what I was starting to get here. Like I was getting both of the elements from here, 1, 3 and 1, 3, 2. So by the way, just in case it's not clear, this is also the same as the left coset 1, 3, 2, h, because this coset contains 1, 3, but it also contains 1, 3, 2. So it looked like I was starting to get this, but then I started getting other things that were most definitely not in that coset, like 2, 3, and 1. And the reason that was happening was because I can't actually make this transition here. I can't take this coset, h1, 3, and turn it into 1, 3h. That's a big no. And the reason is, h is not a normal subgroup. It's not a normal subgroup of S3. And it turns out that the thing that I need, the specific thing that I need to be able to construct this group of cosets and have the operation be well defined, is a normal subgroup. And we're going to prove that in the next video.